So I know you can do all the definitions. If a reaction is determined to be spontaneous at 25 degrees, does that mean it will automatically happen when you mix the reactants at 25 degrees? No. Spontaneous just means it keeps going after you meet the activation energy. You still have to meet the activation energy, and then it will continue to go. Okay? Number 3, a reaction has a positive delta H. Is it exothermic or endothermic? Yeah, you better know that. It's endothermic. Which side do I add it to? The reactant side. Very good. Okay. Number 4, 2 reactions occur and each causes the beaker in which it is done to get hot. The first one gets much hotter than the second, however. The same number of moles of reactants are used in each, and the delta H's are those numbers. Which belongs to the first reaction? The higher number, right? Which in this case is the negative 355 kilojoules per mole, because it feels hotter, so it's releasing more energy. Number 5, okay, use bond energies to determine that. I'm not doing that right now unless you need to see it. Is everybody okay doing the bond energies to figure out your delta H? Remember, with the bond energies, you're always going to do the summation of the reactants minus the summation of products. You're going to work from left to right, only with the bond energies. Everything else, you're going to do the summation of the products minus the summation of the reactants. Okay? Number 5, use the bond energies table on page 420 to determine the enthalpy of the following reaction. And remember, when you're using the bond energies, it's the only time you work from left to right instead of from right to left. Using your chart, if you drew these, you would have, okay, you have to draw it out so that you can see the bonds that you're actually doing. So we did that. Then you look here and you go, okay, first, I have 4 C to H bonds, so 4 moles, and then you look up the C to H bond, and it's 410 kilojoules per mole. Okay, then you have 1, 2, 3 moles of this, 3 moles, and you look up the chlorine to chlorine bond, and it's 243 kilojoules per mole. Minus, now we're over here, we have 3 moles of the Cl and 1 mole of the hydrogen to carbon. So let's do the 1 mole first. 1 mole, the hydrogen to carbon is 410 kilojoules per mole. Plus, because I've got this in a bracket, we have 3 moles of the chlorine to carbon, which is 330 kilojoules per mole. And then plus, we have 3 moles of the hydrogen to chlorine, which is 432 kilojoules per mole. Ran out of board, didn't I? My church actually bought this board for me just to do chemistry on. There's no other board this big in this building. Okay, and so once you do all that, you end up this turning into 2370 kilojoules, because the moles cancel, minus 2700 kilojoules. But here, the significant figures goes to this place. So I'm going to just put a line under it to help myself. So this is 2370 kilojoules. This is 2700 kilojoules, but it goes to the tenths place, just like this one does. So the answer is actually negative 330 kilojoules, because that goes to the tenths place, and it's an exothermic reaction because we got a negative delta H. Okay, so that's how you do number 5. You'd have to do the Lewis structures so that you could see the bonds. Thank God he's not going to give you too many of those. And the good news is they're not as accurate. That's why they don't torture you with more of those. Okay, number 6. The enthalpy of the following reaction is negative 137 kilojoules. What is the energy of the C triple bond end bond? Okay, so it's given to us there. And so what you can do is go ahead and work the bonds. So we're going to go from left to right here too. So we have 1 mole of the H to C bond. And if you look that up, it's 410 kilojoules per mole. And then you're looking for that next bond, and there's only 1 mole of that. So I'm going to go ahead and put it here, 1 mole of the C triple bond N. That's what we're looking for, right? And that'll be in kilojoules per mole. That's what we're looking for there. Plus 2 moles of the hydrogen to hydrogen, which is 436 kilojoules per mole. Minus, now we're on the other side, we have 3 carbons to hydrogens, so 3 moles, and you look up the carbon to hydrogen, it's 410 kilojoules per mole plus. And then we have a carbon to nitrogen, so we have 1 mole of that. I'm going to bring it over here. 1 mole of the carbon to nitrogen, which is 300 kilojoules per mole, plus I have 2 nitrogen to hydrogen attachments, 2 moles of, that is a 390 kilojoule per mole. There you go. So you're going to add all that craziness up and solve for this guy. And that's how you're going to get your answer. And your answer is going to be 900 kilojoules. Okay, this gets a little weird on the significant figures. You'll end up finally getting down to this bond, which is what you're looking for, equals, and then you end up with negative 137 kilojoules plus 2 significant figures on this one, so it's 1,000 is 2 significant figures, so it's 1.0 times 10 to the 3rd kilojoules, okay? And that's all over per mole. But I want you to look at this. We have 1,000, but to the 2nd significant figure, and we're adding to it 137. And so this is going to give us, are we subtracting that? Yes, this is negative. Silly me. Negative. So we're subtracting that. So it's going to give us 900, 800, and 1,000 minus 137 equals 863. It's going to give us 863, but our significant figures has to be to the 100th place. So our answer has to be 900 kilojoules per mole. And that's why, if you left it like this, it would be wrong. You have to watch those significant figures. You really do have to watch them. And so that dropped us down to 1 significant figure. Number 7, what is the standard enthalpy of formation of iron solid? That's in its elemental state. What is its enthalpy? It's good. Number 8, it says, what is the enthalpy for the complete combustion of? And we have C6H6 liquid. And it's at 25 degrees, so we know we can use Hess's law. Okay, so we're going to go ahead and do the complete combustion, so that would be plus O2 gas, and that's going to yield CO2 gas plus H2O gas, and we have that memorized because we know how to do a complete combustion reaction. Okay, so then we're going to balance it, so we're going to go, well, I have to have 6 of these, and I have to have 3 of these, and so that's going to give me 15 of those, so I'm going to put 15 over 2 here, and then I have to get rid of that, so I'm going to go times 2, 15, 12, 6. And then let's check it. We have 12. I didn't do that right. Did I? 6 times 2. Right. Yeah, it was. Okay, that's right. It is 12. I'm looking at this. Shame on me. Thank you. And then 12, 12, and then 6. And 24 is 30 and 30. Okay, good. We're balanced. So far, so good. Then you use Hess's law to figure out, so I've got to go back to that page. You use Hess's law to figure out the enthalpy of formation, okay? And that's on page 424. So you do the products. So we have 12, I'm having trouble here. We have 12 moles of CO2 gas. So we look at the chart, find CO2 gas, and it is negative 393.5. And notice this is kilojoules per mole, okay? Plus, we got to do 6 waters, and they are, 6 moles, shame on me, moles. And water in its vapor state is negative 241.8 kilojoules per mole. And then minus 2 moles C6H, right one, there it is, in the gas form, 82.6 kilojoules per mole. Oh, is it liquid? And I looked at the gas. You're right. Thank you so much. It is in liquid form. So be careful of that on your test, that you look for the right one. It's a good mistake to see so that you don't make it. So we have 49.0 kilojoules per mole. There we go. Thanks for that help. Okay, now notice, some of these have negative signs and some of them have positive signs. So you're going to have to be careful. You're going to have to work very carefully. As you do that, it's number 8. I end up getting negative 6270.8. I'm going to write it here. Here, I'll put it here. Equals negative 6270.8 kilojoules per, whoops, just kilojoules. We killed the moles, didn't we? We went like this. Yep. And we have to go to the tenths place because all of them went to the tenths place, and we're adding or subtracting, aren't we? So our answer has to be to the tenths place. So far, so good. Now, am I going to add this to the reactant side or the product side? It's going to go, it's going to go this way. Okay, this is exothermic, which means it's going to give off that energy. So we are going to add it to the product side. We just lose the sign and add it to the product side. Okay? So far, so good. Now, the next part on number 9, it says, nope, it goes to something different. Goes to something different. Ah, there it is. Okay, number 9. We're going to do 9 and 10. That's probably where we should have gone in the first place. It's all good. Number 9. It says the enthalpy for the following reaction is 157.9 kilojoules at 25 degrees. So let's just go to number 10 because that's all the information we need. So we have C, which is graphite, plus 2H2S gas yields CS2 gas plus 2H2 gas. Okay, I want you to notice something here. That's in its elemental form. That's in its elemental form, right? This is really not hard. So when you look at number 9, and it said that the following reaction is 159.7 kilojoules at 25 degrees, where am I going to add it to? Which side? It's 159 kilojoules. Which side is it going on? Come on, it's 159 kilojoules. It's going to be a reactant because it's positive, so it's an endothermic reaction, so it's going to be added over here. So I'm going to go ahead and I'm going to add it over here. 157.9 kilojoules. Okay, that's the information that's given in number 9. And then it says, what is the delta H formation of this? Well, actually, that's not hard because you know that it's 157.9 kilojoules equals, it's the products, which we have 1 mole of CS2. So I got to go back to my little Hess's chart. There it is on page 424. And I find CS2 gas. Is this one a gas? Yay, it is. And so it's 116.9. 116.9 kilojoules per mole okay, minus whatever 2 moles of the formation enthalpy of H2S is, right? Which is what we're looking for. You could just call this X if you like. Be a lot cleaner, okay? Okay, so when you do the math on that, this enthalpy is going to end up giving you negative 20.5 kilojoules per mole. If you did the math on this, it would give you a negative 20.5 kilojoules per mole for that. Now, that was number 9. Let's do number 10. You really don't need that information for number 10, but I just wanted to show it to you since we were so close anyway. Okay, so on number 10, I'm just going to remove this. On number 10, this is the information from number 9. And it said, how much energy would it take to make 100 grams of CS2? So we want to know, if we want to make 100 grams of this, how much of this would it require? Correct? There's your setup, just the old style setup. So you're going to start where you don't have a question mark, you're going to drive to where you do, and you're going to use the mole bridge to get there, correct? Stoichiometry. So you're going to go, all right, well, I have 100 grams of CS2 times line grams of CS2 moles of CS2. Hopefully you guys haven't forgotten how to do that. What are these? Thank you. What is it? 76.13. Thank you very much. Okay, and so that gives us, what does that give us? Okay, I have done it. Hang on. I just got to find it here. Okay, 8, 9. Here we go. 1.314. 1.314 moles of CS2. Now, we're going to go across the mole bridge. We're going to go from here to here, right? We know that when we do this, I got to ditch that. We know that when we do this, we've got the moles of whatever, because this has to go here. And we're trying to get to the kilojoules, aren't we? That's where we're going. We go, okay, there's a 1 here, so there has to be a 1 here. And in front of kilojoules, I have 157.9. See it? It's the same way as doing the stoichiometry. Just because it's a weird number, don't let it freak you out. You handle it just like you handle other stoichiometry, okay? Okay. So then we have 4 significant figures both places. So that's going to end up giving us 207.5 kilojoules, because this will cancel and you're left with your kilojoules. Number 11, draw a reaction coordinate diagram for each of the following situations. Don't put numbers in. Leave the energy axis unnumbered. Okay, so in other words, you're just supposed to show them if it's going uphill, downhill, etc. So the first one, it's exothermic, and it has a high activation energy. So it's exothermic, so it's going to start higher than it ends, and then it's got a large activation energy, something like that, right? And then the second one, it's endothermic with an activation energy that's only a bit larger than its enthalpy. So here, you're going to have something like that, right? Okay, not a bunch, and it's, yeah. And then the last one, it says a reaction that's much easier to start, but it releases more energy. So much easier to start, but it releases more energy. Something like that. Is everybody okay on doing those? So you got to kind of think through it to do that. Okay, turn the page. Number 12, for each letter below, choose the situation that has more entropy. A vase sitting on a shelf, or that same vase broken into many pieces. Good. Not good, but yes, more entropy. B, a sample of water as a liquid at 0 degrees, or the same mass of water as an ice cube at 0 degrees. The liquid, definitely. C, a copper pipe that is cold, or the same copper pipe that is hot. The hot one. D, a bunch of confetti scattered evenly on the floor, or a 3 by 3 meter room, or the same amount of spaghetti, confetti done on a 2 by 2 room.
3 by 3.
Good. The 3 by 3 has more entropy because it's more space. Thank you. Number 13, a student says that because a chemical reaction has a negative entropy, change in entropy, it cannot be spontaneous. Is that person correct? Why or why not? No, because the second law applies to the whole universe, not to individual systems, right? Okay, number 14, determine the delta S of the following reactions. First one goes from gases to a solid on the right-hand side. Is the delta S positive or negative? It's negative. It's decreasing, isn't it? It's becoming more orderly, therefore the entropy is decreasing. Remember, think of it that way, okay? So the next one, it's got 3 moles of gas going to 1 mole of gas. Is the entropy increasing or decreasing? Decreasing. Decreasing, so it's going to be negative again, isn't it? And then we have a solid and an aqueous going to an aqueous and a gas. Do we have entropy increasing or decreasing? Increasing, so it's going to be positive. Thank you. Number 15, you calculate the delta H for the complete combustion of that. Determine the delta S for the same reaction. You're just going to do it the same way. You're going to go to the chart. You're going to do the summation of the products minus the summation of the reactants. Only this time, those things in their elemental form are on the chart. Remember, everything has got an entropy. Okay, so it's on the chart. And remember, all joules per mole Kelvin. So watch your units on this test, please. Number 15. And problem 8, you calculated the enthalpy for the complete combustion of C2H6 at 25 degrees. Determine the entropy for the same reaction. So let's look back to number 8. We have to do the complete combustion reaction again. So on number 8, we had 6H6 liquid. Complete combustion. CO2. Okay. We have 6 of these. We have 3 of these. That is 12 plus 3 is 15. 15 over 2. Okay, so now we have 12 of those, 12 of those, 12 of those, 12 of those, and we have 24 plus 6 is 30 and 30. Okay, we're balanced. Now, we are doing the enthalpy, and we're going to use the chart. Remember, you work from the products, the sum of the products minus the sum of the reactants, and you're going to use your chart. So it's just going to be 12 moles, and you go on your entropy chart, and it is 213.7 joules per mole. And remember, per mole Kelvin, and remember, this is a gas, so you have to look it up in your gas phase. Yeah, but it's given to you there. Okay, plus 6 moles times water in the vapor state, and so water in its vapor state is 188.7 joules per mole Kelvin, minus, now we go over there and we have 2 moles of C6H6 liquid, which is 173.4 joules per mole Kelvin, minus, I'm just distributing right now, 15 moles of O2 gas is 205. Let's see. 15 moles, 205.0. And that's joules, moles, Kelvin. Okay. And so you do all that, and you end up getting yep, 278.4 joules per Kelvin, because the moles will cancel. And you have 4 significant figures everywhere, so that's why. 16, use the Hess's law technique to calculate the delta G of the complete combustion of the thing we just did at 25 degrees. Is the reaction spontaneous? Okay, this is very similar to what you just did, only now you're going to use the Gibbs free energy formation. So you're just going to go 12 moles, and you use the Gibbs free energy chart. You find CO2 gas. It's negative 394.4. And this time, though, it's kilojoules per mole. And then plus, and you're going to go 6 waters in the vapor form, and so you find water in the vapor form on that chart, and it's negative 228.6. Make sure you find the one that's in the correct phase because the numbers are different. Minus, and then you're going to go 2 moles, and that is 129.7 kilojoules per mole. And then you're going to go minus 15 moles, and then you look for oxygen in the, well, that's always going to be a gas, isn't it? Oh, the oxygen is in its elemental form, and so it zeroes out. Yay! So we don't have the oxygen. Yay, yay, yay. Only in the entropy does it not zero out. And so that is going to end up giving you an answer of negative 6353.2 joules, because all your moles will cancel. And because it's a negative number, the reaction is spontaneous. And so your answer would be yes. And that is a lot of work to get an answer of yes. 17. Okay. The enthalpy and change in entropy of several reactions are given below. For each reaction, determine whether it is spontaneous at all temperatures, never spontaneous no matter what the temperature, or spontaneous for a range of temperatures. If it is spontaneous for a range of temperatures, give the range. Okay, now, thanks to a student in class, Molly, we determined that when they have the same sign, you have to figure it out. You have to do the math and figure it out. But if they have opposite signs, then there is a definitive answer. You can look at it and figure out it's going to be spontaneous or it's not going to be spontaneous.
Opposite, you'll have a definitive answer.
Yes.
And if it's not, if it's the same, you won't have a definitive answer.
If it's opposite,
So like if it's,
oh, I like it. You're right. If they're opposite, you have a definitive answer. You're right. Do you see that? Oh, thank you for simplifying that. Does everybody see that? So if these signs are opposite, it's either going to always be spontaneous or never be spontaneous. And then you can, oh, God bless your soul. Okay. And then if it's not, if they're the same, then you're going to have to figure it out. Oh, good. Okay. And so the first one and the last one you have to figure out. And if you did the math on those, you would just do the delta G, and you're trying to figure out if it's spontaneous, so actually you're going to make it less than 0. So if they are opposite signs, there's a definitive answer, yes or no. You don't have to do calculations. But if they're the same sign, then you're going to have to do calculations to figure it out. Okay. So the first one, they have the same sign, don't they? And so we're going to have to calculate it. And so we're going to use delta G equals and the enthalpy minus the temperature in Kelvin times delta S, right? Okay, so here we are given 146.1 kilojoules minus, we're looking for the temperature at which this could possibly be spontaneous, and times 86.1 joules per Kelvin. Well, we can't do that. So you know what, let's go ahead and convert this one to joules also. So I'm going to go ahead and go I'm going to put 146.1, I'm just going to really cheat and make it easy, times 10 to the third, and that would be joules, right? Okay, now, if you do this and you solve for T, you end up with T is greater than 1.70 times 10 to the third Kelvin. And that is where this reaction would be spontaneous. Because remember, to be spontaneous, delta G has to be negative. So that would be the answer for A. For B, they're both negative, and therefore it is actually spontaneous at all temperatures, because if you put the negative in here and the negative in here, then if you put the negative in here and the positive in here, it would give you a negative delta G, so it would be spontaneous at all temperatures. Okay, I just want to make sure you see that, because this stuff's on your test. On B, this they give you a negative for, minus the temperature, and then this they give you a positive for, which means that whatever that is, it's going to be a negative minus a positive, and so it's going to give you a negative delta G. That's good. So that's spontaneous at all temperatures. C, there's a positive enthalpy minus, and then whatever the temperature is, and a negative of this. This is going to be plus a plus. So it's going to be a positive delta G. So this one is not spontaneous at all temperatures. It is not spontaneous, and that's true at all temperatures. That would be C. D, once again, they have the same signs, so there's not a definitive answer that you can just come up with like that. You have to actually do the calculation. And so once again, and we are given this as negative 19.4, and I'm going to go ahead and take it to joules, minus, we're looking for the temperature, and then we have a negative 114.1 joules per Kelvin. This would give us a temperature of less than 3670 Kelvin. And so at less than 3670 Kelvin, it would be spontaneous. 18, which of the following is not zero for an element in its natural phase? Good, the entropy. Number 19, you and your friend are going to the store. You each leave at the same time and take a different route to get there. You arrive before your friend. Which of the following is a state function? The path you traveled, the time you took, or your destination? Destination. Number 20, a physical process in a system cools its surroundings and is spontaneous. Does it result in an increase or a decrease of entropy for the system? Now think, the system cools, which means it's giving off energy, all right? If the system cools, it's giving off energy, then it's an increase in entropy because it's giving off energy, right? Got it? Are we going to get there? Guys, 4 more weeks, 2 more chapters. Okay? Be blessed. Take your test. Be done with this. I'll see you next week.